morning, everybody. Morning. This morning we're going to talk about air conditioning. Isn't that? Good times. So this morning I want to talk about overload, which we already talked about a little bit recently, but I also want to talk about safety tripping. Because in both of these cases, we want to find the cause rather than expecting that some magical force caused it to trip and now it's fine, whatever it is. So I want to talk through that a little bit. So what do you think, let's start with the compressor. What do you think is the primary reason, or some of the primary reasons, that a compressor will go out on internal overload or trip on overload? I'm just going to draw pictures while you're thinking. Let's get some theories here. Anybody know what that is?
Switch.
What type of switch?
Safety switch.
Hold on. Is it normally closed or normally open?
Normally closed.
It's normally closed. Open on rise. Temperature switch. So this is your traditional good old-fashioned thermal overload. So what makes a thermal overload trip? Temperature. It gets too hot, right? Good morning, Jessica.
Good morning.
How was Guy Penrod?
Amazing.
Good. I couldn't make it.
Too bad.
I know. How was his hair?
Amazing.
Good. Good.
Very Moses.
Good. Ooh, good times. All right, so what causes a thermal overload inside a compressor to open? Overheating. What are some of the reasons? What are some of the things that cause a compressor to overheat? Ooh, okay, we jumped right to it. So we'll just say fan shutting off. Okay, that's a good one. What else? Oh, overcharge. Okay. We'll talk about that one. What else? Undercharge. What else?
It was a great idea.
What did he say?
I said undercharge, and he just took it. Low
Huh?
capacitor.
All right. We could have a low or failed capacitor. Okay. What?
The suction. How about service valve is not open.
Suction service valve closed. Okay.
Had it happen one time, but rare, but also freezing.
I'm not going to do that. You just liked it. This is your thing.
I think that's error number 3. That's the thing that
All right, so we can argue. I'll stand close to you at the end and we'll argue about your silly little thing you like to bring up that never actually happened. Okay, what else?
It's really good handwriting, by the way.
You know what?
Unusual for him. I can read it. No, this is great.
Uh-huh.
Right.
Okay.
Practicing.
All right. Enough about me. Let's talk about you and talk about your needs. All right, how about dirty condenser? That's one. So if you run into a compressor that is going out on thermal overload, what are you going to find? What is it going to be doing? Well, what will be off? Hold on, what will be off?
Fan will be running.
The fan will be running, generally speaking, and the compressor will be running. Will not be running, sorry, opposite. Twist it, turn it around, other way. So what would happen, though, is there a case where you could have a compressor out in thermal overload where neither would be running?
Yes.
And what would that be? If you have a fan motor that's not running, and that's the reason why the compressor is overheated. So there are cases where you're going to walk up on a unit, the fan motor will be off, the compressor will be off, but the compressor's off because the fan motor's off. The thermal overload in the compressor is tripped because you don't have a condenser fan.
You replace the capacitor, fan comes on, the compressor does not.
Yes. Yes, that's also a common one. Yeah, your capacitor is failed, your fan wasn't running, your compressor was running, especially when you have a separate fan and compressor capacitor rather than a dual, and your compressor's still overheated. Now you got to cool that down. All right. So let's talk through these though a little bit. So if you have a compressor overheat due to a fan shutting off intermittently though, what would that look like? Anybody ever had that happen? Mm-hmm. Yeah? On what?
Service call?
A service call. That is a place where that happens. It is a place where that happens. I meant what type of system. I should have been more specific.
What type of system?
Yeah, what type of system did you have this happen on?
Oh, sheesh, I don't remember.
You don't remember? Okay. It happens a lot on Lennox units in VistaK. So I thought that's what you were going to say because it happens so many times there. Why, you're looking at me like you don't believe me.
I'm looking at you like I've never had that happen.
You haven't?
Okay.
That was like totally a thing. Jeez. All right. Well, whatever.
You know, intermittent fan issues, and it would trip the
High pressure switch.
high pressure switch,
Yeah.
and then it would be on lockout. But
Right.
you wouldn't find the compressor overheated.
Okay.
because
Good
of the
point.
safety
Good point. Good point. That was high pressure switch. I'm getting ahead of myself.
People were always confused because the LEDs were backwards.
That is annoying too.
So instead of it being
Wow.
high pressure, it showed low pressure.
We're really bagging on Lennox right now.
What was the reason?
They're a moneymaker.
What?
What was the reason for that?
Okay, so the reason is that it was just a case of where the condenser fan motors that they used, they were clamshell motors. They were low horsepower motors. I think they were like 6th or 8th horsepower, something like that. And they would just go out on overload. And I think it was probably bearing failure that was going on, but it wasn't instantaneous. It wasn't like it would be completely locked. You could still spin it. It would just overload on hot days. It may have been something in the design, how it was dissipating heat, who knows, but they would just overheat. And it's an irritating problem because you walk up on the unit. In that case, your high pressure switch is tripped. Let's draw a high pressure switch here.
Well, it's not tripped anymore.
Correct. Okay, good point. You walk up on a system, it's out on high pressure lockout. This is actually a good example. This is a good one to kind of riff on a little bit. So you show up, the board is showing, if the LEDs are in the right order, the board is showing that you're out on high pressure lockout, but as soon as you reset power, it comes right back on. So because it comes out of lockout, defrost board comes out of lockout, now it's running. And when you test it, everything tests normal, like you would expect it to. Your gauges literally have a big message on it that says normal. All is normal. The robotic voice on your gauges shouts at you. No, you take all your measurements, you measure your amperages, there's nothing that's really outside of what you would expect. But the message here is something caused that. Something caused that high pressure switch to trip. Now, for a newer technician, what are you prone to assume when you run into that circumstance? You walk up, it shows it's out on high pressure, the board's blinking codes, you reset the power, comes on. Well, you can blame magic, especially if you're near the Magic Kingdom.
What would you quote?
I just winked at the camera.
What would you quote, Matt?
Yeah, what would you quote, Matt?
What would I call it?
Yeah, new system?
Is that a dig on Friday?
No, I don't know. I don't know what happened on Friday.
No, so I would
Trying to get some.
just reset and then further test the system to see any further issues that are going on.
Right, but what happens if you further test the system and you can't find any other issues that are going on?
Back call Sam.
Call Sam, and then what does Sam say?
Sorry, I was on a meeting. What was we talking about?
All right. So the point is that what you don't blame is the pressure switch, because that's what people would tend to do. They'd be like, oh, this pressure switch, something's wrong with it. So bypassing it, that would be an obvious no-no, which some technicians would do. None of you, I'm sure. You don't bypass safeties, right? But the other would be, okay, well, there's probably something wrong in the safety switch, and then once you replace that and it does it again, oh, it's probably the board. But it usually isn't the safety switch or the board in intermittent problems like this. A really common intermittent problem is a mechanical failure that takes a while to occur. It's actually more common than anything else. And in a circumstance like the one we just talked about, condensing fan motor overheat, where the condensing fan motor runs a while, then eventually it gets hot enough that its thermal overload trips, then that takes out the high pressure switch or the compressor thermal overload. Are you kind of getting your head around what we're talking about here? So what I'm wanting you to think is a couple layers deep on these problems. But obviously first, if you show up, we're going to go back to compressor overheat. You show up, this thermal overload is tripped. Something happened that made this compressor run hot, and either it was really hot for a short period of time, or it was pretty hot for a long period of time. And that's actually a key distinction, because when you go up to a compressor and it's going in and out of thermal overload, like you can actually watch it happen. You hear that that kind of thing that it does, and I'm doing this. This is the amperage going up. See, that's what this is. That would be a locked compressor. But most often, why does a compressor do that? What's the most common reason on the systems we work on that a compressor does what I just described? Bad capacitor, right? Could be wiring issues too. Could be the wire going to the capacitor is burned off, or a terminal, going to the compressor, the terminal lead is melted off. Could be that. But usually it's a capacitor or a wiring issue, most commonly. And then it's a mechanically locked compressor. But why is it able to do it so quickly? Why can it reset so quick? Because normally, if you have a compressor that's overheated because of like being low on charge or something, you got to run a hose on it in order to get the thing to reset, or let it sit for hours and hours and hours. But why, in the case of a failed capacitor, does it reset so quickly?
It's not as hot inside.
What?
It's not as hot inside.
It's more hot. It's hotter, but the heat is isolated in the windings where the thermal overload is. So it's actually higher temperature, but it's right where that thermal overload is. So if you think of a compressor, don't just think of one. Let me draw you a really bad cartoon of one. You have your suction line. I had to make a little gap there so the Freon could make it in. Otherwise, look. Now the Freon's going to make it out over here. Oh, I can't cap the ends, otherwise it can't make it out the end of the line there. All right, so your suction gas comes in to your compressor and it falls down into the bottom of the compressor. It goes in, we're going to draw this as a scroll here. Oh, look at this scroll. Ooh, look at this. There's a motor down here. Ooh, look at there. So it pumps it out of the compressor, out the top. If there's a mechanical issue way up here, and the heat is happening up in the top of the compressor, it's going to require that it heats up the whole compressor before it gets down to where the thermal overload is, somewhere in this area, behind the compressor terminals and the windings. So when you have a mechanical problem, even a failed condenser fan motor or a compressor that's got something going on in the head, or maybe it's high head pressure, dirty condenser, any of those types of issues, the entire compressor is going to have to get hot, the shell, the whole thing, before it trips that thermal overload. Now, there are actually some compressor manufacturers nowadays that certain types of mechanical problems, like when they unload or little ports or whatever, will actually overload and redirect some of that hot gas right to the thermal overload. Like they actually, when it has certain conditions, it actually tries to blow that discharge gas right on the thermal overload so it trips quicker. So you don't have to heat up the whole compressor, which is why you'll notice some compressors cool down quicker than others. You have some older models of compressors that you work on that just seem like they always take forever. And it has to do with the thermal mass of the compressor as well as some of those internal designs. But the point being that when you have a wiring problem or a locked compressor or any of those sorts of things where the compressor isn't running and overheating, it's just the windings are heating up, it resets pretty quick. That's why when you have a failed capacitor, which we have all the time, have you ever wondered why you don't have to run water on a compressor in order to get it running again after a failed capacitor? Or generally you don't? Even though that compressor was sitting there going out on thermal limit. It's because that heat was isolated to the motor windings down at the bottom of the compressor. So the point being, what I'm getting at here is you can actually tell a little bit about what might be going on just by how quickly it's resetting. If you have a compressor that's taken forever to reset that thermal overload, that's an indication that it was a running fault, meaning that it sat there and it was running for a long time, and that entire shell was getting hot, and all that thermal mass heated up. Make sense? So things like fan shutting off, overcharge, undercharge, suction service valve closed, still has to heat up the whole inside of the compressor, dirty condenser. Now,
Yeah.
what happened?
How did the suction service valve close get on there?
Right, and you rejected it's
What was his?
frozen.
We're not talking about his yet, because his is a complicated situation. All right, we need to give it a second. We need to think, and we need to catch our breath, and then we'll get there. All right. So first off, I want to address this quickly before we move on to other safeties, this overcharge and undercharge. So why could undercharge cause a compressor to overheat? Because it's a refrigerant-cooled compressor, right? And so if you have less mass, lower mass flow rate, then your compressor is going to run hot. It requires the refrigerant mass returning on what line? Suction line, right? So your suction pressure matters as far as compressor temperature. If you have really low suction pressure, that means you have low mass flow rate. That means you don't have as many molecules moving through that compressor, and that's going to result in high temperature. Also, high compression ratio. So if you have low suction pressure and high head pressure, that also causes a compressor to run hot. So if you think of it in very simple terms, when you have low suction pressure, that causes a compressor to run hot, and when you have high head pressure, that causes a compressor to run hot. Yes?
Isn't the amperage lower on undercharge sometimes though?
Amperage, yes, and those two things aren't the same. So the idea that overheating always comes with overamperage is not correct. In this particular case, when you can have a case where you've got low mass flow rate, meaning you don't have a lot of refrigerant moving into that compressor, and your compressor will draw lower amperage, lower current. You could have a case where your compressor is drawing lower than normal current and still overheating over time. And that's the difference between overheating because of an electrical problem, like we talked about, overheating in the motor, versus it overheating because it's not being cooled properly. And in the case of low suction pressure, low mass flow rate, it's just not being cooled properly. You don't have enough stuff moving across that compressor and across that motor to keep it cool. Make sense? It's like saying, I think an easy way to think of it is, think of your engine on your car. Your engine could overheat because something is broken in the engine. And that engine is having to work too hard because there's issues with the, whatever, piston, cylinders, crank, anything mechanical with the, wait, we're getting there. And then you could have a problem with your engine overheating because of the coolant system, because you're not circulating enough coolant through. You could be low on coolant, whatever. And so think of refrigerant in this case as your coolant system for your compressor. And then you have all of the mechanicals inside the compressor that can also result in overheating. So in cases of high current problems in the compressor can cause the compressor to run hot, but that could be because of mechanical failure in the compressor, or it could be because of a really big compression ratio or a really high head pressure, right? So kind of different things there. How much work is the compressor having to do results in current, less work, less current, more current. But then also the cooling side of it is a little bit separate than that, which is why both overcharge and undercharge can both cause a compressor to overheat for different reasons, right? Undercharge is because you don't have enough cooling. Overcharge results in that compressor having to do too much work and being overloaded. You can actually have cases like where in refrigeration where systems come out of defrost and the compressor can overload because the suction pressure is too high. It's trying to do too much work. That would be too high of current. So we literally can overheat a compressor or overload a compressor because our suction pressure is too low or because it's too high. Either one. Too high because it has to do too much work. Too low because that causes it to overheat eventually because it's not cooling it well enough. Does that make sense? Everybody follow that? Okay. Now again, you have to get to the extreme side of these before it happens. It's not like a tiny bit of undercharge is going to cause the compressor to overheat. It's not like a tiny bit of overcharge is going to cause that to happen. They tend to be on the further edges of that. But some more common ones would be like the fan shutting off. Well, when the fan shuts off, what happens? When your condenser fan shuts off, what happens? Head pressure goes sky high, right? And why does it go sky high? Because it can't reject heat. The condenser is the heat rejector. Its job is to get the heat out of the refrigerant. If that heat stays in that refrigerant, this comes down to basic pressure and temperature relationships. Increases in temperature result in what? Increase in pressure, right? And so as that temperature, as that heat remains in there, that temperature just keeps going higher and higher. That heat can't be rejected out. That pressure also just keeps going higher and higher. And as it does that, the compressor is doing more and more work. It's pushing against more and more. And then depending on the design of that compressor, there's also going to be additional re-expansion inside the cylinders. If you have a reciprocating compressor, it's really easy to imagine this. It has to pull down far enough in order to pull suction gas in, and then as it pushes up, then it discharges out. But there's always a little bit of refrigerant left in the top of that head when it takes the downstroke again. And so if that is really high pressure, really high temperature gas, that's going to run hotter because now you're re-expanding that higher pressure, higher temperature gas back into the compressor again. Versus like a scroll or rotary compressor where it's continuous compression. So there are some variances in that depending on the technology. All right. Any questions about that? So you got a compressor going on thermal overload. What's going to happen? It's going to be shutting off. It's going to be trying to, if it's locked, it's going to be trying to start and shutting off. If it's running, but it's just overheating because of some of these conditions that during running, it's going to run for a while and then it's going to shut off and then you're going to have to cool it down before it starts again. What is our suggested method of cooling a compressor?
Compressor cooler.
So the cool presser, that little magnet with the hose, that's one thing you can do. You can run a hose on it. Just keep in mind that when you run a hose on it, make sure that you're not, first off, power's off, and that you're not running a hose anywhere that water shouldn't go, so be careful with that. But also keep in mind that sometimes it takes a long time, and so I don't want you just condemning a compressor because a hose was run on it for an hour and it still didn't reset. In a case like that, we can tell the customer, we're going to quote you a compressor, but this could reset, leave it overnight, try it again in the morning. No? No. Jesse doesn't like it. Let's talk about why Jesse doesn't like it.
Okay, have you ever had a hose on a compressor for an hour and it not reset?
Yes.
And then it reset.
Yes.
Well, I bet it wasn't an hour.
Okay, now part of this may be, I have a couple.
Hose was actually coming
I have a
out.
couple specific instances in my head where this happened. One of them bit me, where another company came back and was like, "There's nothing wrong with this compressor."
Notate, certain compressors do take longer than others.
Right. So this was one of these
Big old
giant
train ones.
recip train orange compressors. Yeah.
The orange ones
Yep.
have a lot of mass.
Yep.
So the total heat content
Right.
is a lot higher.
And I think it also depends on the segment of the industry you're in. So if you're working mostly with smaller compressors, then it's unlikely that you're not going to be able to reset it. If you're working with big commercial compressors, it might be more. So
The reason I don't mind it from a technical standpoint, but the uncertainty you're providing to the client is the main issue that I see in there.
okay.
Especially with the quoted compressor.
Yeah, yeah.
So
That's a whole can of worms you're opening up.
that's fine. All I want is I don't want us condemning compressors when the compressor isn't bad and there's some secondary cause. Because even then, if you replace the compressor, you still haven't solved the secondary cause. So the primary thing to anchor on here is get the darn thing reset if you can reset it. Don't be impatient with it. Just because, oh, it's still not running, I ran a hose on it for 15 minutes, still not running, it's out on thermal overload, need a new compressor. That's what I don't want you to do.
If you check the windings, what's going to be an indication of that?
Okay, if you check the windings,
That's kind of because that always helped me in the field.
okay. So if you check the windings of a compressor, you've got common, start, and run. Okay? If you measure between your start and run, you're going to measure an ohm reading. There's going to be an ohm measurement if it's out on thermal overload. But there will not be a measurement between start and common and start and run in common. And the reason is that your overload is behind the common terminal. So it's behind the common terminal before the common connects to the two windings. There's only two windings. Common's not a winding. Common's just a terminal, just a point between start and run. So if you imagine, I've got a really good image of this on HVAC School that demonstrates this a lot better, but we'll put that up in the video. But, well, it just happens to be the case. I got this darn good website, you know what I'm saying? So we'll draw it this way. So I'm really bad at drawing windings. Here we go. There's a winding there. And then you have a thermal overload right here. And this is common. Run, start. So when you measure between start and run, you're going to measure our measurement because it doesn't, the thermal overload doesn't break that path. You have your ohm meter between these 2 points, you're not going to measure it. But if you measure here to here, here to here, you will. An easy way to do this, if you have a compressor that you know is out on thermal, and by the way, in cases like this, I want you to be down at the compressor terminals. I do not want you doing this at the contactor. I get lots of guys who are like, well, it's easier to do it at the contactor. If you do that as part of your diagnostic process, that's fine. But I want the top off, set over in the grass, not tilted up with the wires bent, and you're bending the fan blade, and take it off. Unwire it, put it in the grass, go down to the compressor, open up where the terminals are, inspect the terminals, that's the main reason why, and then I want you to do these tests at the terminals. So if it's individual connectors, I take a picture of it first to make sure you don't miswire them. Same thing with the fan. If you're new to it, just take a picture real quick, unwire it, do it at the terminals. Because I don't want any sort of, well, the wire wasn't on all the way or whatever to get in the way of this procedure. So then you take your leads and you measure across. So you're going to read ohms here. You're not going to. Then leave your ohm meter in between two of these. Just take two of your leads with alligator clips, clip it between, say, common and run, put it on ringer mode, set your meter up here, and so then as you're resetting it, you're going to know as soon as it resets, because your meter is going to be quiet, and then as soon as that thermal overload resets, now you know it's reset. So you don't have to do that whole like, well, let's see if it works now. No. Let's see if it works now. No. But when you have this, where you're measuring ohms between start and run, but not between run and common or start and common, you have an open thermal overload. And I would say 98% of the time, that is a statistical statistic that I just made up, 98% of the time it will reset. Are there cases where you just happen to show up at the time that it just decided not to reset? Sure. But guess how the compressor will feel if that's the case?
Hot.
Wrong. Cold. Meaning that if you...
Said it just showed up.
Well, I'm just saying, I mean, okay, it didn't just decide. I'm saying that if finally the thing didn't reset once, when you walk up to that compressor, it's going to be cold in the first place. The odds that you walked up to it, it was hot, you cool it, and this time it just didn't reset, it's not going to happen.
And I wouldn't even say hot. I would say if there's any warmth.
Any warmth at all.
At all.
Right. Imagine you've got a body,
Been trying to run.
and it's been dead 3 hours. There's still a little warmth in it, you know, even if it has that much warmth.
Okay, now I understand.
It clicked.
Now Kyle just got it.
One thing that I do on those, that I've done on those big orange ones,
Mm-hmm.
is I'm cooling it down,
Uh-huh.
and then it doesn't come back on.
Yeah.
Let it sit for about 5-10 minutes, and then go touch it again. Because sometimes right after you put the water on it, the outer shell is cold, and you try to start
Mm-hmm.
it. But if it still has internal heat, if you let it sit for 5 or 10 minutes, and you go back and touch it again, it'll be warm.
Mm-hmm.
Yeah. But then you know you're not.
Those orangies, man, let me tell you. Let me tell you, built like little tanks. All right. This same principle goes for other types of safeties. High pressure switch, most of the same things we just talked about. You got a high pressure switch tripping, they don't just trip by themselves. Got a low pressure switch tripping, they don't just trip by themselves. Loss of charge switch, same thing. Now, if you walk up to a switch and literally it has physical damage to it, it's actually damaged in some way. There's cases where pressure switches will leak, for example, and yeah, then they have to be replaced. But the amount of times I've had to replace a bad pressure switch, even if you do, which it happens, but even if you do, it's because it's been tripping. So now, not only do you have to replace the pressure switch, you got to figure out why it was tripping in the first place. So in a case like that, if you go to a job and you are 100% confident that a safety or a pressure switch has failed, you are 100% confident. Now, I want to be really careful about what I'm about to say here, because I'm not saying to jump things out and leave them that way, and I'm not saying to do anything unsafe. But what I am going to say is, go ahead and jump it out so that you can figure out what caused it to fail in the first place. Do it safely. With gas, you would have to be really careful. Like, don't jump out a rollout switch, because, you know, I don't want it to roll out in your face. But figure out what caused that safety to fail before you just ordered the safety. Do you all understand what I'm saying? So if it's a high limit on a furnace, for example, figure out why it was tripping on high limit, because the high limit doesn't just fail. If it's a high pressure switch, figure out why the high pressure switch was tripping, why it failed open, because they don't just fail. They fail because they've been smacking open and closed so much. Same thing with the thermal overload. If you find a compressor that is truly failed because of an open thermal overload, you still better figure out what else. And this is the reason why I was suggesting what I was suggesting with the compressor, even with the customer, is that we got to have a conversation with that customer, because the odds that that's all that's wrong, pretty much zero. I mean, not zero, but close to zero. That all that's wrong was a compressor with an open thermal overload, because that compressor open thermal overload happened because of low charge, overcharge, dirty condenser, whatever.
It could be something as simple as you bumped the float switch and the fan was running backwards.
Yeah, and that can happen. This is actually, it could be something as simple as you bumped the float switch and it was a scroll compressor, and the scroll compressor started running backwards until it went out on thermal. And I've had so many people tell me that that's impossible and that doesn't happen, and it's, anybody here seen that happen before? Just all the hands are raised. It happens. So, and it happens because in a compressor, in a scroll compressor, you have some sort of a discharge valve here that shuts off to prevent backflow, but you still have a pocket of high pressure here. And when that thing short cycles, where it goes on and off that quick, that pocket of high pressure is equalizing back through, and then when it starts up, it runs backwards. Now, it doesn't happen on all brands. There's one particular brand that does it worse than others, but it can happen. And if that happens, you could literally have this sequence of events where you end up replacing a compressor because you just accidentally short-cycled it. And you don't want to do that. Stop it. Take some time. Figure out the cause. Always be focused on the cause. And this is how I want to end this class. Anytime there's a safety, and a thermal overload is a form of a safety, anytime there's a safety that's open, yes, diagnose what safety is open, good job, use your meter, all that stuff. But even more important is what caused the safety to open. Why did that happen in the first place? Now we're going to get to Bert's controversial freezing units causing compressors to overheat baloney. Go ahead, Bert.
What happens to a TXV when the coil's encased in ice?
All right, coils encased in ice, what happens to the TXV? Anybody else want to answer, or do you want me to answer? Okay, I'll answer. The TXV closes, Bert.
Okay, so it's not that uncommon to find a compressor overheated because of low refrigerant mass on a frozen coil.
Frozen evaporator coil. Who else has seen a compressor overheated with a frozen evaporator coil? You have. Okay.
He's got Bert.
You haven't seen it, Jesse?
Not completely frozen. Like, I've seen frozen coils, but usually that's due to low charge.
With the compressor overheated.
Yes, due to low charge.
So I'm going to add that I believe that it can
I
happen.
remember it happening when you were training me. All
Oh,
the time.
wow. Okay. Every day. Okay. So
Yeah, I mean, like, it's unique. Like, it's multiple circumstances kind
Right,
of.
long
Like,
line
I
set.
think it could be like
in that.
long line set,
Yeah.
slightly dirty evaporator coil, and low charge, like combination.
yeah, and that's what I'm suggesting, is that do I think there can be a case where a system could be frozen and you show up and the compressor's out on thermal overload? Yes, because mass flow is a big factor in keeping a compressor cool. But I think it's very unlikely on a typical system that has a proper charge, right, and a frozen evaporator coil and a normal length line set. I think it's much more likely that it's a combination of you picking up heat in the suction line in addition to being low on charge, in addition to a frozen evaporator coil. And we've talked about this, like we know in our market especially, you can have frozen evaporator coils due to low charge, for example, where some people will argue that can't happen. Well, we see it all the time. Airflow, though, is one of the primary causes, and there are these kind of two competing things that cause compressor overheat.
A lot of times when the ice is built up around it, the air doesn't pass over the compressor and cool it.
So when you're thinking about this potential issue, are you thinking that the ice getting on the
There's no ice outside.
Right. There's no ice outside.
No, the ice getting on the TXV.
My guess is
and then
that's what's
slamming down.
That's my guess, because there's just such a low volume on the suction. It's not unusual to have a frozen system and a warm suction.
Okay.
Sure, that can happen, but again, it depends on when you catch it, what the core problem is that caused it to freeze in the first place. So is the core problem that caused it to freeze airflow? Then I think it's very unlikely that this is going to happen. If the core problem that caused it to freeze was low on charge or a restricted metering device potentially, sure, you could get such low mass flow rate, because that's what we're saying. We're saying that our mass flow rate is very low. Such low mass flow rate that you can get some freezing at the start of that evaporator coil, but by the time it gets out to the compressor, you're saying a complete block of ice.
This is only going to happen if there was an issue, like maybe a slightly restricted TXV,
Okay.
or slightly low on charge, and you have a lot of ice, because then the problem gets suddenly worse, and you show up and the compressor's overheated.
Okay. I think this is very rare, and I think what I don't want people doing.
Every day.
I mean, if it's overheated, it's overheated, right? I mean, that's if it.
Obviously, I'm running too many calls a day.
If the, I'm overworking you. If the compressor's overheated, it's overheated, and if that's the symptom that you see, then sure. I mean, I would still check everything else, like dirty condenser coil, make sure your fan's not going off, all those other things, because I don't think most of the time when your compressor's overheated, it's going to be because your coil's a block of ice. That seems. As in, like, I've also run a lot of service calls, and I've never had that happen, so maybe this problem just really likes you. It's possible.
A lot of people get distracted by the ice and they don't check the compressor, but I always ohm it out every time, and you'll find that it's overheated a lot when there's ice on the coil.
That's good.
It may have seemed like it was running just fine, but I went out and I ohmed it, and the thing had an open thermal overload. Is that what? Ignore all of what just happened here, please. All right. So the message is, to end, anytime you have an open thermal, anytime you have an open safety, find the reason why it opened. Don't just believe in magic that it opened because sometimes they just open, because they don't. They can fail for other reasons, things can happen, but when they fail because they've been opening and closing, and safeties ain't supposed to open and close. Make sense?
Right.
Great. Have a wonderful week. Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.